So now that we've defined a Markov reward process, let's complicate it a little bit. We want to add agency in this, in the fact that we, as an agent doing the reinforcement learning, need to learn how to perform actions. And the way we do that is we add another thing into our Markov reward process to make it a decision process, right? And that's basically a set of actions. The only thing that really changes here is that our transition probability matrix and our reward function are now going to be indexed by actions as well, right? So what we're basically saying here is that from particular state S, I'm going to take a transition, and this transition could be one of many, okay? And all of these would be different actions at different indexes, like index 1, index 2, index n, okay? And they would lead to different states, okay? Subsequently, S1, S2 here, and S3, okay? And we can do that very easily and then go to a new state. And then the rewards could also be changed on and predicated on the combination of the origin state as well as the action that we take. We're not actually going to use this differing reward value for this part of the MVP process that we're talking about now, but we will later on. So with this in mind, we can revisit our student Markov reward process that we had earlier. And just note, even though this is very similar to the previous diagram, it differs in a couple different ways. For example, over here, it doesn't have the extra unit for the pass. Okay, it's gone because we can think of it as a deterministic process. Once we enter pass, we're going to go directly to sleep, and so we can align that arc. It's just that the reward here is a plus 10 instead of, in that case, it was a plus 10 with a minus 2 for studying. So that would have been a plus 8. Also over here, we have some differential rewards. Here we can see leaving state, this state here, which was our first unit, of course, and going to our second unit, we have a minus 2, but perhaps going this way to browse Instagram would cost us a reward of minus 1 here, meaning maybe not as taxing in terms of what we had to do. Okay, and you'll notice this particular edge, right, to go clubbing, we said maybe going clubbing gives us a little bit more energy, so we might get a plus 1 there. But now, this particular action leads to different states as a consequence, right? So we're going to say that we deterministically take this action, but which state will end up is a stochastic problem, right? So we might end up here and decide not by our choice, but by the environment's choice, whether we're going to go end up back in the first unit, the second unit, or back in the third unit of our course. And so we've pretty much left out all of the action nodes. All of the action nodes are these filled dots that you can see here and over here, when there's only one action that leads deterministically to the state. So we can just write this entire edge as a plain edge, as you'll see in the next couple of slides, and only use the one case down here where we say the action of going clubbing has a stochastic effect, right? We don't know exactly which state we'll end up in afterwards. So with this in mind, we really want to put together a set of actions that's going to be the most optimal for our reinforcement learning agent. And we can think of this as a policy. The policy is basically just a distribution over actions given states. So if I'm in a particular state at a particular time step, I want to know what types of actions can I do from that state at that same time step and make it over a distribution. Now, if there's the best possible policy, we might set this deterministically to say that we only have one particular action that's the most optimal that we want to take, but we can generalize it and think of it as a stochastic variable in which we have a probability of a state, rather a probability of an action rather than a fixed action. We can say that the policy fully defines the behavior of the agent, and that the MDP policy depends on just the current state, right? That's the whole point of making a Markovian assumption, is we only need the current state to determine what to do. And this means that our policies are stationary. They're actually time independent. We don't need to know exactly what time we're in to make that assumption, right? So regardless of when I'm in this particular state, I'm going to carry out the action dependent on the policy. So one of the really nice things about an MDP is you can flatten it back into an MRP pretty easily. The way we do this is by getting rid of our actions, right? We're going to factor it out by taking the idea of the policy dictating what the agent is going to do, right? You can say that, again, the state sequence that we have that we're actually going to traverse our MRP, our flattened MRP, is also a Markov process, right? So we have a state sequence S1 through all the way through Sn. We're going to encode that in this vector, a script S, and we're going to have a transition matrix P, but it's now going to be predicated on our policy. And that's going to change the way we calculate our our state transition matrix and our reward process to be factoring in what we would do given the policy, right? So the way we define the state transition matrix is going from S to S prime here, any of the states here, conditioned on the policy, where we're going to take a look at all of the different actions that we are going to do, defined as the policy, and multiply that against the original state transition matrix with the policy action taken into account. And that's going to be the same thing that we're going to do with reward. So this is basically going to average through our state transition matrix and our reward matrix, factoring into account what the policy says we're going to do. So in order to get closer to solving an MDP, we're going to have to define what the policy is. And how do we do that? Well, we have to go back to figure out what is the reward at each time step. And we can do that by introducing the two value functions, but now they're conditional on the policy. So state value function here is the same as before, but now we're indexing it using a subscript for the policy, which is basically saying what is the expected return, just like before, but following a certain policy once we're at state S, okay? So this is just going to be the expectation under the actions given by the policy for the average return, the expected return, when we're at this particular state S, okay? And the same for the action value function. Here we're not looking at the state, but the action going out of the state, okay? It's just going to be the same. It's going to be this Q value with respect to the policy, given the pair of the state and the action. That means, again, from this state, taking this particular action, what's this value? And that's just going to be the expected value of the returns, just like before on top, when we take this action from this state, okay? So now we can look back at our student MDP and look at the state value function that we might calculate, right? Here we have to set a policy, remember that, because we have this pi here. And so we're going to say, for this particular diagram here, we're going to look at a uniform policy, all right? So for all of the different actions that we can take, they're just going to be a uniform case. Most of these have two particular actions, like for example here, we have two particular actions, either going to sleep or study, or from here, going to study for the final and pass the course, or going clubbing, okay? And so the only case where this is not true is in this sleep state here, right? Because this is a terminal state, there's nothing else that we can do, okay? And we're going to also use a discount factor of 1. What does this mean? This means we're going to allow the rewards to cascade for all of the timestamps without penalty, right? And you can see what's going on here. If we're in this state here, we have the expected value of a state value function of 7.4, because obviously I can study and pass the course with a reward of 10, but I also might go clubbing, receive a +1, but I might probably end up in a state where I'm going to have to incur some negative costs to make it back here. Okay, so you can see that these numbers play out pretty well. You can see going back, it gets lower and lower until it gets negative. Here it's negative because there's a good chance, 50-50 chance here, that I might go browse Instagram and lose some time in this loop over here. So we've replaced the transition probabilities with the ones that are dictated by our policy. Remember, in the earlier MRP, we had probabilities attached to them. Now we're defining those probabilities using our policy instead.